Hello everyone. In this tutorial video we are going to talk about how to perform scientific calculations, which do differ slightly from the work that we're used to doing in math class. We're going to cover two main topics, and those are the use of significant figures in calculations, as well as the formatting that we use in science for multiplication and division problems, which is called dimensional analysis. So to get started with significant figures, there's one fairly straightforward rule, and that is you should keep the smallest number of significant figures provided in the problem. So what this means is that regardless of what your answer comes out as in your calculator, you're going to need to round it to an appropriate number of significant figures. Let's look at some examples. So let's say I have in my problem the number 8.32, and I am told to multiply or add that to 1.2. When I type this into my calculator says that the answer to this question is 9.52, which makes sense. However, we need to go back and talk about significant figures. So from the original problem, 8.32 has 3 sig figs. It has 3 non-zero digits, so each of them are significant. 1.2, also from the original problem, only has 2 significant figures. And since 2 is the smaller number, we are going to need to round our answer so that it has 2 significant figures. Just like in normal rounding, I'm going to start with my largest digit, my leftmost digit, in this case 9. It is going to be significant. My next significant digit is going to be 5, and then I need to decide how to round. I'm going to base that decision off of the digit that I am not including in my final answer, the next digit. Just like in normal rounding, a 5 and up would cause us to round up, but since this is a 2, we are going to round down. And this means that we are going to report our answer as 9.5. instead of 9.52. Notice that our final answer also has 2 significant figures, just like 1.2 did from our original problem. Another example would be if we were to take 2.25 and multiply it by 3.1. When we plug that into our calculator says that the answer to this is 6.975. However, 2.25 has 3 sig figs, and 3.1 has only 2 sig figs. Our answer currently has 4 significant figures, so we really need to round it. Again, we're only allowed to have 2 significant figures because that is the smallest number of significant figures that we were provided in the problem. So I'm going to get to keep my 6, and I'm going to get to keep my 9, and then I'm going to look at the 7 to decide whether I round up or down. 7 says to round up. And when I round 6.9 up, that would round up to 7. Now I can't just report 7, because I'm supposed to have 2 significant figures in my answer. So in this case, I must include the 0 after the decimal so that I have my required 2 significant figures. If I just wrote 7, that would only have 1 significant figure, and it would not be an accurate reporting of my work. Let's look at a third example. If we do 7.50 times 1.2, our calculator tells us that the answer to that is 9. 7.50 has 3 sig figs because the 0 is to the right of the decimal and the right of the number. 1.2 has 2 sig figs, and so that means that our answer needs to be reported with 2 sig figs because it is the smallest number of significant figures from the problem. Right now, our answer has only 1 significant figure. So just like when we were talking about rounding to 7, we're going to need to report this as 9.0 so that it has the 2 sig figs required by the problem. So just to review, when working with significant figures, you should keep the smallest number of significant figures provided in the problem, and you have to match that number of significant figures in your rounded answer. So if your answer comes out with fewer significant figures than necessary, you're going to need to add a 0. It just so happens that in each of these examples, the smallest number of significant figures was 2. That is not always the case. You should look carefully at each individual problem and decide how many significant figures you are provided in each number. Now we're going to talk about dimensional analysis, which my very first chemistry teacher taught me to call railroad tracks, so that's still what I call them now. Dimensional analysis is used for showing multiplication and division work. So we might get an example problem that looks like this. We might be asked to find the volume of 7.0 grams of a material with a density of 3.5 grams per centimeter cubed. In the past, many people might have written this work out as 7.0 grams times the ratio of 3.5 grams for every 1 centimeter cubed. Now the reason that I have flipped over this ratio from the way it is presented in the problem is so that grams will be both in the numerator and the denominator, and I can cancel it, leaving me with centimeters cubed as the unit of my answer. I would plug this into my calculator and it would come out as 2. I would go to my original problem and say that 7.0 has 2 sig figs and 3.5 also has 2 sig figs. So that means I need to round my final answer to 2.0 so that it also has 2 sig figs to match the numbers in my problem. Now, dimensional analysis looks very similar to this method of writing out your work. We start with a large horizontal bar. It looks kind of like a fraction bar. And we put the number that we are provided with in the problem in the upper left-hand corner. We then draw a vertical space instead of a multiplication sign. We draw a vertical line instead of a multiplication sign, and then plug our ratio in right behind that. Just like in the old work, I'm going to cross out my units that cancel, and any units that remain will be the units of my answer. Just like in the old work, I need to make sure that my significant figures in my answer match the significant figures from the problem, so I would include 2.0 as my final answer. When you're doing a single-step multiplication problem, dimensional analysis doesn't save you a lot of space and time. But if you have a multi-step problem, for example, find the mass of 2.5 milliliters of a 7.25 gram per centimeter cubed material. Dimensional analysis does become more helpful. So again, we're going to draw a long horizontal line, and we're going to place our number from our problem in the top left corner there. We're going to draw a vertical line instead of a multiplication symbol, and then we're going to get ready to include our first ratio. I would like to use the density so that I can get to my unit of mass, grams. However, if I include the units of density right here, milliliters and centimeters cubed are not going to cancel. So instead, I'm going to pull a ratio from the units of volume lab that 1 milliliter is equivalent to 1 centimeter cubed, and I'm going to use that ratio instead. So I'm going to write it in so that milliliters will cancel, and I'll be left with centimeters cubed. By placing milliliters in the denominator, I have 1 in the numerator and 1 in the denominator, so they will cancel. And then I can use my ratio from the problem, my density ratio. And I can write 7.25 grams for every 1 centimeter cubed, and centimeters cubed will cancel out. This leaves me with 18.75 grams. Notice that grams are the only unit that didn't cancel, so they are the unit of my answer. And then I need to check my significant figures. So 2.5 has only 2 significant figures. 7.25 has 3. So that means that my answer needs to have 2 significant figures in it. One thing to note is that ratios that we memorize to convert between units do not impact the significant figures of our answer. So we would only be looking at the numbers provided in the original problem, the measurements in the original problem, in order to determine the significant figures in our answer. So I'll have my 1 and I'll have my 8, and then I'm going to look at my 7 to decide which way I round. The 7 says I need to round up, so that means I'm going to report 19 grams as my final answer for this question. In this multi-step multiplication problem, we can start to see where dimensional analysis will save us time and space, as we have several ratios lined up and we are multiplying and dividing across. When you go to enter into your calculator a situation like this, I would type in 2.5 times 1 times 7.25, multiplying across the top, and then I would divide by all of the numbers in the bottom. In this case, they're both 1s. Now, those of us who are more comfortable with math will recognize that times 1 divided by 1 divided by 1 are not going to change the value of our number, and so might not be necessary. Either way, when you type them in, you're going to get 18.75 out of your calculator, and then you need to round it to the appropriate number of significant figures. Okay, so in this tutorial video, we have talked about doing scientific calculations. We have talked about the significant figures and the rules for maintaining the smallest number of significant figures provided in the problem. And we've also looked at 2 examples of how to do dimensional analysis, which I mostly call railroad tracks. Thank you very much and have a nice day.